Hey everyone, looking at 5.4. This is on sampling distributions and the central limit theorem. This section's important in that we're going to be using concepts from this section in chapter 6 and beyond. So it takes a little while to lay the groundwork for this, so bear with me. It's a little confusing at first, but we'll get it. Let's talk about sampling distributions. And if we read this, it says a sampling distribution is a probability distribution of some sample statistic, for example, like a mean, that is formed when samples of size n are repeatedly taken from a population. So if that sample statistic is the sample mean, the distribution is called sampling distribution of sample means. What? Okay, sampling distribution of sample means. Let's take an example. Let's talk about a college, and let's talk about the age of the students at the college. Okay, there is a definite population mean. If we take all of the students at that college and average their ages together, we would have the true population parameter. So for argument's sake, let's just say that that population mean is 25 years old. Now, what happens if we just start taking samples of size n from the population and finding the sample of that little sample size? Let's say take 2 students. Okay, so we're going to take 2 students at a time, and then we're going to average those 2 students' ages together and then plot them on a graph, right? So we have a number line here. And that's what this kind of graphic is. Right here's all the little sample. We're taking 2 students at a time. So that's the idea behind that. Okay, so let's say we take 2 students, we average their ages together, and we get 23. And then I'm going to plot a dot at 23. Then we take 2 new students, average their 2 ages together, and we get 27. So I'm going to plot a dot at 27, etc., etc. I want to know what happens to the shape. If I keep doing this many times, what happens to that shape of the distribution? This distribution, if I have dots everywhere, or let's just say it kind of ends up like this, right? This would be called the sampling distribution of sample means. It's how those sample means are distributed when we plot them on a graph. To get an idea of some of the characteristics of this distribution, we can use some StatCrunch to explore a little bit further, and then we'll get into some formulas and examples. So let me share with you StatCrunch. And there is a sampling distribution applet, which looks like this. If you want to play around with it, it's just under applets and down sampling distributions. Okay, so we're just going to explore with this. Okay, so suppose this graph is the distribution of all students at the college, where we know the true population mean is 25, and let's say the standard deviation is 5. What we're doing is we're going to take 2 students, that's that right there, and then average their ages together. So let's do it one time. There's the 2 students, and then there's their average age, right? So it looks like we got a couple of students here in their 20s, averaged it, and we got a mean of 25. Okay, we're going to do that again. 2 new students, average. 2 new students, take their average. 2 new students, take their average. You get the idea. Let's do this many times. So I'm going to do this 1,000 times, right? 1,000 times. I'm going to randomly select 2 students and average those 2 ages together. And I get this. What we're interested in here is the shape of this sampling distribution, right? The distribution of sample means. And I can see here that it looks bell-shaped as well. I mean, it's not perfect because this is a simulation, but I can definitely see a nice bell-shaped curve forming here. Okay. What happens though, maybe the original population was not bell-shaped. right? So what I can come back up here and I can reset this, and I actually can draw my own distribution. So maybe it's skewed to the right a little bit. A lot of younger ages at this college, not too many older ages, right? Let's make it even more extreme. Well, that's pretty good. Okay, let's just try this. Right there. Okay. And then again, let's do 1,000 times. Okay, I can see here now that the distribution kind of matches the original distribution, looks a little skewed to the right as well. But what if we pump up our sample size? So instead of 2 students, we're going to take 50 students at a time. So if I did that once, right, there's all 50 ages, and then I'm averaging all 50 ages to get one mean, right? And then if I do that 1,000 times, oh, look, now I get a bell-shaped curve, right? There's no more skew to it, right? So if I have a large enough sample size, doesn't matter what the shape of the original population distribution looks like, your sampling distribution is normal or bell-shaped. That's an important concept in statistics that you will see pop up time and time again as we go through these chapters. Okay, let's get back to the handout. Hopefully that helps get a little bit of the concept of what we're doing. Now we're going to fold in some formulas. Oh, one other thing before we go back, one thing to notice, the population mean, 20.8, and the mean of the sample means is the same, right? The population mean equals the mean of the sample means. That's a formula I'm going to show you. The standard deviation started at 6.99 on this one, has gone down to 1. So the standard deviation goes down. There's actually a formula that relates those two standard deviations. Again, this is the population standard deviation up here. This is the standard deviation of the distribution of sample means. Okay, so good stuff, right? All right, so back to the handout and we can look at those formulas. They're pretty easy to use, which is good. The formulas themselves are not too bad. So we have what's called the central limit theorem, okay? And there's 2 factors that we just saw. This is just written out nicely, right? So if the population is normally distributed, if you start with that nice bell-shaped distribution, then the sampling distribution of sample means is also normally distributed, and that's for any size, and we did size 2 and saw that if you started with a bell-shaped, you got a bell-shaped when you did the experiment, okay? When we did something that was not normally distributed, we had to pump it up. So, and turns out a fact is in statistics, as long as you have a sample size of 30 or more, then if you draw from any population, doesn't matter the shape of the distribution for that population, then the sampling distribution is going to be about bell-shaped. The greater the sample size, the better, but at least 30 does the trick. The formulas are here. So turns out the mean of the sample means is equal to the population mean. We saw that in that simulation, right? And then here's the one that relates the standard deviations. The standard deviation of the sample means is going to be the sigma divided by square root of n, where sigma is the population standard deviation. Those are going to be 2 formulas that we'll use. One more formula is for a z-score. So you're going to have to find a z-score in these problems, and they're similar to what we did in 5.2. Right, it looks kind of like that same structure. We've got though x bar, and then we have that mu sub x bar. Let's blow this up a little bit. Mu sub x bar we just saw is the same as mu. So this simplifies just to mu right there. And then sigma sub x bar we just saw has its own little formula. That's sigma divided by the square root of n. So I would use this form of the formula when you're finding a z-score. Anytime you're finding a z-score in 5.4, use this and you'll get it right, okay? And we'll do some examples now. Okay, so let's run through the examples on this page. Let's say that the mean IQ for a population is 100 and standard deviation is 15. Find mu sub x bar. Well, we know mu sub x bar is the same as mu, so it's 100, right? Because that is mu, that's sigma right there. Right? Sigma sub x bar are going to take a little more work because that's sigma divided by the square root of n. Sigma is 15. 20 people are selected, that's the n. So 15 divided by the square root of 20. Let's take a look at that. That's about 3.354. Okay, it says round to 1 decimal place, so we're just going to go a 3.4. Okay. And then question B, what is the probability? As soon as it starts asking you what is the probability, you're probably going to have this two-step process where you're going to have to find the z-score first and then convert that z-score into an area under the standard normal distribution using StatCrunch or the table. Okay, so first find the z-score. And we're going to use this formula up here, right? Okay. For x bar, always look to the question. This one's talking about the mean being greater than 110. So I'm going to use 110 for the x bar. The sample mean is 100. The population mean is 100. And then sigma divided by square root of n. We saw that as 3.4, or I could just type it in right here as just 15 divided by square root of 20. The reason for that is because this was rounded, and so if I want to keep it more accurate, I would probably want to just leave it 15 divided by the square root of 20. Now, when you're calculating this, use parentheses in your calculator. I'm going to bring up a TI-84 on my screen now and show you how I would type that all in at once. That might help, and most calculators would be similar. So what I'm going to do is use my parentheses. I'm going to do parenthesis and then 110 minus 100 divided by, and then open a new parenthesis for the bottom, right? And then I'm going to do 15, and then there's another division down there, right? And then I got to hit the square root, so that's going to be second square root, and then I'll type in 20, and then I got to get out of that square root, so just arrow over, and then I'll close my parenthesis. That's how you're going to want to type it in to get it all done at once. And so this is 2.98. Okay, so approximately 2.98. Now I've got to convert that to an area under the standard normal distribution. So that's either table or StatCrunch. Personally, I prefer StatCrunch. So I'm gonna go over here to StatCrunch and try it. Remember that's under stat, calculators, normal, greater than 2.98. Compute, all right? And I'm getting 0.001. So my answer for this problem is 0.0014, or a very low chance of that occurring. Okay, I'm going to stop there, trying to keep these videos under 15 minutes. I'll continue in the next one. Okay, hope that helps. Bye.